This video begins with a problem that we looked at similar to yesterday's class. So it says here 18x to the 4 minus 21x squared plus 3 equals 0. Anytime you see that equals 0, that means we are solving. We are going all the way to find out where this fourth degree polynomial hits the x-axis. So we're after the roots here. So, from yesterday, if you notice, this is a polynomial fourth degree. It has 3 terms in it, but it doesn't look like the traditional quadratic that we're used to factoring. So we can rewrite it to make it look like a quadratic, something like this, where we can now substitute u in for x squared. So if we let u equal x squared and we replace x squared with u, we can see that we have 18u squared minus 21u plus 3 equaling 0. This is of the format from our fourth unit, which was all quadratics. So now what we could do is we can factor. The first rule of all factoring problems is to look for a GCF. I see a GCF here of positive 3, so we can go ahead and factor it out. Okay. Now we need to factor 6u squared minus 7u plus 1. So what we could do is we could set up our parentheses, and I go with the guess and check method. So let's see, I need 6u squared. I need to get negative 7 in the middle, and I need positive 1 on the ends here. And they both need to be negative because my sum needs to be negative on the inside. So let's see, how can I get a positive 1 here? What if I did 6u and 1u? The outside terms would be negative 6u. The inside term would be negative 1. That works. That works. Okay. As we were saying yesterday, the problem began with x. It needs to end in x. You can't stop with the u here. So what we'll do at this moment is replace our u with x squared again. Now you could do this at the very end if you were to just solve for u at this point, get u isolated, then bring back the x squared. That's totally fine. That's totally fine. But for me, I suppose I like to put it back here now in factored form, just so I could see what's going on. Now, what we'll do is we'll set every factor equal to 0. And we'll solve. Notice the GCF is just a constant. 3 equals 0 is a false statement. We can ignore it. Let's go ahead and isolate the x variable in the second factor. We'll take our 1 and add it over. We'll then divide by 6 to create a fraction 1 over 6. And then we will go ahead now and take the square root of both sides. Now when we take the square root of 1 over 6, we take the square root of 1 over the square root of 6, that equals 1 over root 6. We can rationalize that by multiplying the top and the bottom by the square root of 6, leaving us with a plus and minus root 6 over 6. Those are 2 of our 4 solutions. Now over here on the other side, the third factor, we can isolate it to create x squared equaling 1. Take the square root of both sides. The square root of 1 is plus and minus 1. We're not concerned with just the principal root. We have to consider both instances here. So we have a fourth degree polynomial with 4 real solutions. 2 of them are rational, and looks like the other 2 are irrational. So that is how you solve a polynomial of the form 18x to the 4 minus 21x squared plus 3. So what I'd like you to do now, I'd like for you, if you haven't already, go ahead and pause the video, attempt this problem, and then go ahead, press play, and then watch me work through it, and then we can kind of compare our answers 4x to the 4 minus 14x squared plus 12 equaling 0. So go ahead and pause the video, try it, and then come back. First things first is let's go ahead and rewrite this as a quadratic. I will say that this is x squared minus 14 quantity x squared plus 12. And then here again, we'll let u equal x squared. And we'll rewrite it 4u squared minus 14u plus 12 equaling 0. The same as the previous problem, we have a GCF here. Remember, guys, when you factor any polynomial of any degree, you have to first look for that GCF. In this example, the GCF is 2. Looks like I could take a 2 out of everything. It just helps out with the factoring. It decreases the numbers and therefore the trial and errors. It decreases the trials that you have to try when you go ahead and factor something like this. So 2u and u, because 2 is prime, those are my only options there. Now 6, I have options. I could do 1 and 6, 6 and 1, 2 and 3, 3 and 2. Let's see, I need a negative 7 in the middle, a negative sum but a positive product, so both of my factors here should be negative. And let's see, how can I do this? If I do 3 times 2 on the outside, that'll give me 4u, negative 4u, and then negative 3u. Yep, on the inside, that'll give me the negative 7 that I need. As before, let's go ahead and replace our u with x squared. At this moment, you can replace it, or you can go ahead and replace it at the end. It doesn't matter. It doesn't matter. All right, setting everything equal to 0. All of our factors equal 0. We're trying to figure out what our roots are. The key word in the directions are solve. And what you need to look out for, again, is that equals 0. If it just says factor, okay, if it just says factor, we would have been done right here. But it didn't say factor, it said solve, so we have to go all the way through and solve. So here we are. The GCF is 2 equaling 0. That's inconclusive there. It doesn't mean anything for us. 2x squared. Let's move on to the next factor. We'll isolate the x and find that we will take the square root of 3/2 or 1.5. Some of you guys like to convert everything to decimals, and I suppose that's fine, but you don't have to. If I take the square root of 3/2, that's the square root of 3 over the square root of 2, and if I rationalize to get the radical out from the denominator, I will have multiplied by the square root of 2 over square root of 2, leaving me with the square root of 6 on the top and 2 on the bottom. So those are 2 of my 4 solutions. Off to the last factor, if I take my x squared and add 2 to it, and I take the square root of both sides, x now equals plus and minus the square root of 2. So here, in this example, you have a 4th degree polynomial with 4 irrational real roots. Now here's an application problem. We could use some of the things we've learned in this section to solve a problem like this. A small cube is cut out of a larger cube. The side of a smaller cube is half the size of the side of the larger cube. The volume of the remaining figure is 7,000 cubic centimeters. What were the dimensions of the larger cube and the smaller cube? So what we first need to kind of focus on is the equation for volume of a cube with a length, a width, and a height. So that volume, the equation for the volume is length times width times height. All right, so we have that. We understand that. That's how you find the volume of a cube. Let's see some pieces of information here. So if we take out the smaller cube from the bigger cube, we have 7,000 cubic centimeters remaining. So if I'm trying to figure out the volume of the bigger minus the smaller, it would have to equal the 7,000. So I can write it out like so. The volume of the remaining figure, which was 7,000, we're going to take the volume of the larger cube, okay, the larger minus the smaller. Okay, so this little sliver here. If we took that out from the larger cube, then that would give us the 7,000 that's given to us in the problem. So let's see. The larger cube has a height of x, a width of x, and a length of x as well. So we could say that the volume of the remaining figure is 7,000 cubic centimeters equals the larger one, so x times x times x times x times x, which is x to the third power, minus the dimensions of the smaller cube. So y times y times y. It's y to the third power. Well, we can't really get anywhere here at this moment because we have an equation here in two variables. What if somehow we can create an equation with the same variables? In the given information, it says, hey, the side of the smaller cube is exactly half of the size. So I'm reading the second sentence. The side of the smaller cube is exactly half the size of the side of the larger cube. So in terms of x, y would equal half the amount of x. So 1/2 the amount of x. What if I were to substitute that in for y right here? We would then have everything in terms of x. It may help us solve this problem. So let's go ahead and do that. Instead of saying x to the 3 minus y to the 3, let's say x to the 3 minus, and now this represents the volume of the smaller cube. So if I know that y in terms of x is 1/2 x, well then 1/2 x to the power of 3 would represent its volume. And if I take 1/2 to the power of 3, that's 1/8. And then x to the power of 3 is x to the 3. Now we're getting somewhere. We're getting closer to solving and figuring out what the dimensions of the larger and the smaller cube are. So let's take a look here. How could I go about combining like terms? These are like terms. I have 1x to the third power minus 1/8 x to the third power. Now in terms of 8, I can rewrite 1 as 8/8. 8/8 minus 1/8, I could recreate this term from 2 down to 1 term. It's 7/8 x to the 3. Now my task is to isolate the x variable. So in doing so, I can multiply both sides by 8/7. I can multiply both sides by 8/7. And the 8's cancel or reduce down to 1. So on the right-hand side, I have x to the 3 equals, if I reduce this is 7 into 7,000. This would be 1,000 times 8. So I have 8,000. Okay, so at this moment, we would go ahead and take the cube root of both sides and find that x would equal 20. But what we're going to find out here in the next section, I believe, no, in 2 more sections from now, is if we have a third degree polynomial, we have to consider all options. There may be more than one answer here because it's a third degree polynomial. So with that said, if I were to subtract 8,000 from both sides, I would get x to the 3 minus 8,000. And in this moment, we see that we have two terms and both of them are perfect cubes. And we have an equation for that. We have a property that says, hey, the cube root of x to the 3 is x, and the cube root of 8,000 is 20, so x minus 20 is the initial factor. Following squaring the first one, x squared is x squared. Changing the sign from negative to positive, the product of 20 and x, 20x, and then lastly squaring 20. If I square 20, I should get 400. Now what I need to do is take all of the factors and set them equal to 0. We'll set that one equal to 0 and this one equal to 0. So I have x minus 20 equals 0. There's my 20. There's my 20 centimeters for the larger cube, 20 by 20 by 20. Okay, so the dimensions are 20 centimeter by 20 by 20. And then for the smaller, I said it was half. So the smaller cube is 10 by 10 by 10. Let's talk about this over here. Let's try to factor it. because what we need to do is we need to figure out if we have more than one solution here. And so by setting it equals 0, we're in solve mode, we're in factor mode. I'm going to go ahead and jump right into the quadratic formula because I don't want to try and list out all my factors of 400. Why don't we just jump right to it and see if we could figure out whether or not this is going to have a real solution or not. So negative b plus or minus b squared, so we have 20 squared, which would be 400, minus 4 times a times c. Well, what I want you to take a look at is your discriminant here. This discriminant would be 400 minus 1600. This is negative 1200. We would be taking the square root of a negative value, which is inconclusive. It is, it means that we have complex solutions, right? It means we have complex solutions. So the only one that makes sense here is the 20. And going back up here to the top, if I know that x is equal to 20, then 1/2 of x over here would be 10.